Hi everyone, and welcome to the second class in the series on Introduction to Population Balance Models. Today I will be your speaker, and my name is Michael Ghijs. I work at Biomath and LPPAT at the pharmacy faculty. I'm doing a postdoc right now on the modeling of pharmaceutical processes, and I've applied PBM in my work as I modeled the size change in pharmaceutical granules, so the breakage thereof. So in today's class, we will have a look at the rate processes. Now, whereas Juan Pablo introduced you to the mathematical framework of PBM in the first class, and he told you that it's all about modeling the change in distributions, exactly what today we're going to see is how we implement mechanisms and how we can implement how they affect the distributions. So that's actually what rate processes come down to. Getting from mechanism to something that the PBM can interpret as a change in the distribution over a certain time step. And this will be the input for PBM solution methods, where then it will solve the system over time. This scheme also gives an overview where rate process fit into the PBM modeling paradigm. As in the first class, so system definition and mathematical approach were described broadly. And now we move on to rate process as a way to include the mechanisms that cause change in any distributed property, and how we go from that mechanism to actual PBM language that it can use for solving the system in the solution methods. The latter is for next class. So today, focus on the rate processes. Let's return to the theoretical framework of the population balance equation, and let's see where rate processes fit into this scheme. As you remember, there are three main terms in this equation. On the left, we have the accumulation, or the rate of change, which is the one that we actually want to model by the knowledge that we have on the other processes, on the other terms. So the continuous term, I will not mention this in this class so much. Rather, the discrete term is where the discrete rate processes are drawn into the equation. In this H term, we just find our processes, and that's where we put our knowledge on how distributions change due to our mechanisms. This is rephrased then for the numerics of the PBM, and it's rephrased into birth and death terms. Now, they may sound a bit weird, but it boils down that birth is higher particles or entities appear on the grid because of the mechanisms that you're modeling, and death is the opposite, is the entities that are consumed by the mechanisms that you propose. We will go further in this in the next slides, because we have to take into account that these are numerical concepts that are simply there to translate our mechanism into PBM language, let's say. It amounts to the change in the distribution, so the change in the number density, so the amount of entities you have for each discretization of the coordinates x, r, and in function of time. So birth, again, denotes the number of entities at that time point that are formed by a certain mechanism. And death is the amount of entities that is consumed by this mechanism. We will illustrate this with a few of the most common mechanisms that are implemented in these PBMs in the next slides, so don't worry if it's not very clear yet. And it must be noted that actually for every mechanism, this birth and death concept takes on a different form. For every mechanism, you need to look how is this translated into the appearance and disappearance of entities. Let's have a look at the aggregation process, for example. Aggregation is the process where two particles come together and they stay together to form a larger particle at the end of the simulated step in time. So this means that two smaller particles. So we're, let's say that the only property that we're modeling now is size of the particles. So two smaller ones from smaller classes will come together and stay together to stay as one as the large particle. So upon this event, we have to tell the PVM through birth and death terms which particles were created throughout the step and which particles were consumed. In the birth term, you can see the black dot there. It's the large particle, so this is the one that has been created. So that is being modeled in that step. Whereas in the death part, actually the two original particles should be colored black. Now there's only one to focus on that. But actually both of them should disappear from the simulation, and this should be coined in the death term. So through this step, birth and death step, the PBM knows that in which size classes entities are being formed and where they are disappearing from the grid, from the simulation, due to this aggregation process. In another mechanism, breakage, which is almost the opposite of aggregation, we have the occurrence that a particle breaks and then results in the fragments that it was originally made of. And with breakage, we need to tell the simulation which particles have now disappeared throughout breakage. So the original particles are no longer there in the simulation, whereas the fragments that occur by breakage of that particle should be formed, and the simulation should be aware of that. You can see it again in the black dots. So the birth will result, again, both particles should be colored black, as these are the ones that are appearing in the grid. And in death, we need to tell them that the original particle has disappeared from the simulation in this time step. All right, now let's have a deeper look at the processes that we mentioned, starting with aggregation. Now, we want to look at how mathematically this birth and death concept is being implemented. We see on the top row the H term, so the net change rate in distribution due to aggregation, and it equals the birth minus the death in function of the internal coordinate x, so we're not taking into account the external one for this case, and at a certain time point t. So in the birth term, we need to describe which particles are formed on the grid due to the aggregation of two small particles. So we see on the left-hand side, it is the birth of a particle of size x at time t. That is given by an integral equation. And we first have a look at what is written in this integral. The integral going from 0 to the particle x, so the particle of size x that's being formed. And in essence, under the integral, we look at all the possible combinations that can result in a particle of size x. And when I say size, I mean volume in this case. So we actually go from size 0, which is theoretical, to x, and look at all the combinations that can result in it, and at which rate they are being formed. That's basically it. Now, the rate is given by that term beta. Beta, which is in function of the combination of two particle sizes, in this case x minus epsilon and epsilon, which, if they come together, they create the volume of x, all right, at a certain time t. This is then multiplied with the respective amounts of particles that there are of the respective sizes. So, and the number density of size x minus epsilon at that time multiplied with n of epsilon size at that time. And epsilon is what changes under the integral, so epsilon goes from 0 to x. And if you're still wondering why there is the division by 2 of the overall term, it's simply because we are counting double, in fact, under the integral. because we are going over the combinations, with halfway we actually come across the same combinations, just flipped basically. So we divide by 2 to account for double counting. And then we get for, so the birth term for every size x based on this integral term. And then the death term is similar, but basically the opposite of the birth term. And here we have to look again at the rate at which a certain particle gets caught up in an aggregation and gets combined with other particles of that size. So now the disappearance of particle of size x at time t is the original number thereof multiplied with the integral going from 0 to infinity, theoretically. So practically you will go from the minimum and maximum size of particles that you account for. And under the integral, again, is the beta term multiplied with the density of like the particles that it partners up with to form an aggregation. And you see there's a small mistake there also. In the beta term, there should be as input not only size x, but also size epsilon, as beta is given in function of combination of two sizes. So then we get basically at which rate particles are depleted from the distribution. And beta is often referred to as the aggregation kernel. This is exactly where we can specify the type of aggregation that goes on in our system. This is something that you choose, that you propose for your simulation. Usually this is not well known. And there are different, as we see in the next slide, different types of aggregation kernels depending on how much you already know of your system and which physics do apply. So this is where we implement how things aggregate. Okay, but in general, in the bottom, we can write the theoretical framework as such as we went over in the top of the slide. Back to the kernel, it can actually be written in as a combination of two different factors. So the kernel basically tells us at which rate particles come together of two different sizes and a successful aggregation is formed. So in this occurrence, what should happen? First is that these particles actually meet, and secondly is that when they collide, they stay together. So the aggregation efficiency, or the beta naught term, is the probability that a collision between these particles of size x and epsilon will be successful, at least throughout the time step that is being simulated. And then the collision frequency denotes the frequency at which these particles size x and e meet each other, collide. So the final aggregation kernel is the multiplication of these terms. There are in literature various descriptions of these. On the left-hand side, we see a few that are rather basic and quite often used when there's not a lot of knowledge about the system. And these kernels, the size independent, the sum kernel and product kernel, are then attempted to see if they actually describe the behavior of the real-life system. So the aggregation kernel is usually, in a modeling exercise, a researcher will choose aggregation kernels and will test them, will apply them in the simulation, in the PBM, and then we'll test his model output with real experimental data and see if the aggregation behavior that he has proposed is actually valid there. And the right-hand side, you see a couple of other kernels that are already more based on physics of the system, where this is already more well known. In the breakage mechanism then, again, we need to find the description of our change in distribution, our H term. For every size class x at time t, we need to determine the birth and the death there. In the birth term, we now need to account for the particles that are actually fragments of an originally breaking particle, a larger particle. And that's why in the function description, we go in the integral from the size x, of which the fragments are formed, to infinity to check all these larger particles, when they break, when and at what rate do they result in a fragment of size x. Because that's where there will be new entities, new particles of that size by breakage of the larger one. So under the integral, there are three terms, which is b, the fragment function, s, the selection function, or just the rate at which particles break of a certain size, and finally the number density, so the amount of particles that is a parent of that size. So epsilon will vary from x to the infinity, or the largest particle size that's being modeled. B will tell upon breakage of a particle of size epsilon, with which probability a particle of size x is being formed. Okay, which how many fragments of x are being formed by breakage of a particle of size epsilon. Then there is the breakage rate, or the selection function, so how fast do particles of size epsilon break in this simulation, and then n is the number density, how many particles are there at this time of size epsilon. And by going over that, we find all the fragments that are formed in that time step of size x. Now, the depth term is a lot simpler to model in this case, because now we just need to look at which rate particles get depleted of a certain size. So in this case, we don't even need to use the b term. We simply need to look at the rate at which particles of thus a certain size x break, and how many particles there actually were of that size at that time in the simulation, so at time t. Then, as I mentioned before, we have the the b function, the fragment distribution function, and then the selection function. The breakage kernel is then the general term that's being used to describe this behavior. Aggregation, it's analog to the beta function there. This kernel describes the way in which breakage occurs. So again, you can try as a researcher different proposals for this function and see which one actually fits your model system by checking this with experimental data that you have. So finally, we find a mathematical description for our H term, the net rate of change of the distribution. And as I said, you can implement different types of behavior. This is an example on this slide where we have three types of selection function or breakage rates. So these are described on the left and plotted on the right, where they are plotted in function of the particle size. The size independent is very simple. It's just all particles of all sizes will break at the same rate. And then another one that's very prevalent is the power law description, where you implement this function of selection rate, and now you can still tune a couple of parameters in this function, such as here the S0, the base breakage rate, and the n exponential term. Then there's another exponential function that can also be used, and you can see that these three different functions propose quite different grades of behavior, of breakage behavior in function of particle size. The same goes for the fragment distribution function B. Here you can also implement various types of breakage depending on your system, what you propose. There are a few basic ones, such as the formation of two equal fragments. That one is pretty simple to describe. And another one is the uniform binary kernel, where you actually have an equal probability of all fragments to be formed. So, whereas these two are rather basic kernels, the last one gives already a more in-depth physical description of what goes on, with more parameters to calibrate because this is a more complex behavior. You can see it in the scheme there below. It is that the proposition that when a particle breaks, you get a certain part of attrition, of fine particles that are being formed, and yet another part goes into simply uniform breakage. But in the attrition, you can specify a fragment distribution that's with a normal, the model being modeled with a normal distribution kind of format. Moving on now to another important process that is often being used in this population balance modeling. Nucleation actually denotes where certain particles, certain entities appear on the simulation of the population balance that were not there before. So in the previous processes that we saw, we had a certain balance that we had to adhere to, so no extra material was created in this process. In the aggregation, we deleted the smaller particles that formed the aggregate that is now being and now in the calculation of PBM. Whereas in breakage, we had the original particle that broke, and the original particle has been deleted, and the fragments are on there. But through these processes, the amount of material there, the volume or mass, is still conserved. In nucleation, this is slightly different, as we go from not really zero, but like entities that were not modeled before, like usually really small entities, to some event that creates them and that turns them into entities that are tracked in the population balance. So an example is where, let's say you're modeling a system where there's a certain molten substance that's being solidified and generates particles, let's say. Now, you're not really modeling the melt. There's not a distribution that you're modeling. The distribution that you're modeling is the size distribution of the solidified particles of the melt. So the melt, the liquid, it's not in the simulation until a part of it solidifies and forms a particle that you are actually accounting for because it's a solid particle. So then it comes on the stage of the PBM and then you take it to account. So this is a nucleation process. The same can be said for, let's say, condensation of a gas, where you're not modeling the gas initially, but you are modeling the liquid droplets that are being formed by the gas. So as soon as it condenses, you create some droplets, and then they appear on the grid, on the size distribution that you're modeling in your population balance model. A framework or a physical process where this is all combined, and that accidentally our group at Biomath and the pharmacy faculty are modeling, is the wet granulation process, which in general turns a blend of powder, of dry powder, with the addition of liquid, turns it into granules, so into clusters of particles that are larger and larger and have a certain size distribution. And the phenomena, the mechanisms that occur in this process are various. So as you can see on this scheme, we first have basically a nucleation step where due to the addition of the granulation liquids to the powder particles, which it's just a bunch of powder, it's not part of the simulation yet, but as soon as they are nucleated, they form entities that are being modeled in the population balance model. So these nuclei then go through several mechanisms that shape the final granules that we get out of the system. First, due to growth, which is simply that these particles become larger, but actually they do not take any more mass inside. It's just their volume that is increasing. Whereas in the aggregation stage, so they meet other particles and they collide successfully to come together to form aggregates. Layering can also be seen as some kind of aggregation, but that's more where you already have a larger entity and then small particles are just adhering on the surface of your original particle. And then the reverse can also happen. The breakage can return the aggregated particles into smaller fragments again. Consolidation, finally, is kind of the opposite of growth. It's where your particles, your group of particles gets pressed together to form a smaller agglomerate, but one that's actually more dense as the mass is conserved in this process. So these are typical rate processes that can be found, so mechanisms that create a change in the distribution. And now finally, some of these processes are not really discrete, can also be are actually a continuous process, such as consolidation, the last one mentioned. Now the discrete ones, they either happen or they don't. Upon aggregation, these particles collide and they form a large one. There's nothing like in between. They will not form like a semi-aggregate state or something. That's not being modeled in that process. Whereas consolidation is something that can go on continuously as the volume of a particle can be decreasing continuously throughout the simulation. It's not really an event, a discrete event. It can be upon impact, but that then has to be described within the consolidation depiction, within the consolidation term. For instance, in this case, as you see in the equation, the change in porosity of the particle is being modeled. So the porosity, as you can see, is epsilon in this case, and the change over time of that is modeled by a certain decrease because it's consolidation, so negative rate, and it has certain parameters in this case like compaction rate and a current porosity and a minimum porosity, which difference is taken, and at a certain rate it will diminish, for example. So this is one of the ways in which a consolidation rate can be described. Then next is layering. So this is kind of a mass increase on the surface of modeled particles, and it is layering of fines. So the fines means that in this case these particles are not taking part of the simulation as separate entities. They are too fine to be modeled as separate entities, so they just kind of appear on the surface of the order particles that are being modeled as a layer of powder in this case. You can see there's a specific formula with which this layering process can be described based on the mass of powder. And here there's actually also an increase of mass in the system because you're taking powder that is originally not part of the simulation, but it is there in your physical system, and it gets into the simulation as a layer on top of the other particles that are being modeled and increasing their size. And finally, if we take a look at a process where it's not primarily the size that is being modeled, but let's say the liquid content. So refer to the third point, the drying rewetting stage in a process. Now drying is very familiar. It's the loss of liquid due to the evaporation thereof. And if we want to model this, we can do that by describing, say, the liquid content in the particles. So we arrange the particles according to the distribution, according to their liquid content. And in this case, we have a description from a system of spray granulation where particles of powder are floating, are blown up in the air, are being fluidized. Water is sprayed upon them, but also water is evaporating. And we want to see what is in the end the liquid content distribution throughout these particles. So these are all kinds of processes that, well, in this slide, these processes happen continuously. But important is that we go from the mechanism to a description that physically represents the occurrence of the phenomenon and gives the specifics of how the process actually goes. And finally, this needs to be turned into death and birth terms for the discrete events, and for the continuous processes. This is rather a continuous term, as you can see in these equations. Okay, then with that, I will leave you. This class is continued in the next class, where today's knowledge is being turned into the numerics of a PBM, and where the changes that we've given now in the distribution through the birth and death and this continuous stage are then applied in the core of the PBM, where the distribution is then updated. And Alejandra will give you a very interesting talk about that in the next class. Thank you for listening, and if you have any questions, you can email this to michael.ghijs@ugent.be.